Let me give you a few hints about what you can do when you are solving complicated circuit problems. What you need to do when you see the circuit is to invent some unknown variables that you would like to solve, but you want to make sure that you don't have more than necessary number of unknowns, so you have to choose them to be minimal in number, but you also have to make sure that they are complete, so you have determined all the possible unknowns so that you can relate them to something else in your equations. So after that, after identifying the unknowns, you need to write down the junction rules, Kirchhoff's junction rules, and the loop rules, and then you have a bunch of equations with lots of unknowns in them, and solve them. All right, as an example, let's see this circuit. It's sufficiently complicated. I'm not going to solve the problem, but I'll just illustrate what you can do when you are when you are trying to solve this kind of a problem. This is essentially the Wheatstone bridge problem, right? So if you're not systematic in choosing your variables, then you can easily get lost in these kind of problems. Of course, over the years, people have developed some certain techniques, some certain approaches. I would like to describe two of them. One of them is the most commonly used one, right? What we do in that case is that we choose the currents as on the branches as the variables. So as a result, we are going to assign some currents to each branch, and we have to choose some of them as unknowns. But I would like to choose them in such a way that the junction rule is automatically satisfied. So as a result, I don't have to write down the junction rule when I'm forming my equations. So in that case, I'll just write down the loop rule equations. And in that case, for example, there are 3 loops in here. So as a result, I'm going to have 3 equations, which also means that I should have 3 unknowns. And when you are solving these equations, you can completely determine all the unknowns. So how can you do this? Let me do it like this. So you usually start with a certain branch. Let's say that this branch, I start with this one. So I draw an arrow, and then I say that the current in that branch is equal to I. Right? So that also implies that the current in the lower branch, it is the same branch essentially, is I. So that's one of the unknowns. And then we have a junction in here. So this current is divided into these 2 parts. So as a result, I need a new variable in here. So let's call the current that's flowing over the resistor R1 as I1. Okay. In that case, since the junction rule must be automatically satisfied, I'm not going to give a new name. I'm not going to invent a new unknown to denote the current on the 3rd branch. I just show that it is equal to I minus I1. So as a result, I still have 2 unknowns. With these 2 unknowns, I can express the currents that are connected to that currents on branches that are connected to that junction. So therefore, on this junction, the junction rule is satisfied, right? So as a result, I don't need to write down the junction rule in there. So on this branch, I need to do this again. So as a result, let's see, the current in this branch is I2. So therefore, this is an unknown. So therefore, the current in that branch would be I1 minus I2. Okay, so I minus I1 is coming from over R3. So this branch, let me also write this thing down. So that's I minus I1. So this current and that current, they just join in this branch and then flow in the downward direction. So as a result, again, I don't need to invent a new unknown. The sum of these 2 currents would be the current in here. So this is going to be I minus I2 then. Okay, again, on that branch, the current is I minus I2. So these 2 currents join in this branch and then continue as the current I. So that means at that point the junction rule is again satisfied. So as a result, for all junctions, the junction rule is satisfied. So for this reason, I don't need to check the junction rule anymore. So the unknowns in that case, there are three unknowns. So that's I1, and I2. Okay, and after that, of course, I need to write down the loop rule equations. As I have said, we have three loops in here. So let me show them with this highlighter. That's the first loop. That's the second loop, and that's the third loop. I'm not going to write down the equations. We have seen how to write down the loop rule equations, but once you write down the loop rule equations, you should have three equations together with three unknowns. With these three unknowns, you can solve these three equations and then solve for the whole circuit. Let me show you a practical way of assigning current variables to the branches of that circuit. Okay, this is a method that a lot of people use. First, I'm going to show you the main idea. So I'm going to assign a current distribution on branches which satisfy the junction rule, but this is not necessarily a solution of a given circuit problem. So just consider a current assignment such that the current is flowing only on that loop. So only on those branches the current is flowing, and the value of the current is I1. And there are no currents in these other branches. So in all of these branches, there are no currents. So there's just a current that's flowing in this big loop that I have shown. This is an assignment of current that satisfies the junction rule. Right? So at every junction, the junction rule is satisfied. Okay. So that's one possible assignment. There's another possible assignment. So let me erase this and then show the other possibility. Right? This is the other one. So on that loop only, there's a current flowing, and I'm going to call that current as I2. In that case, only on these branches there will be current. I have just drawn this in the opposite way, but doesn't matter. So there's going to be a current flowing on this branch, and in all other branches, in this, that, and that branch, and that as well, there are no currents. So that's also an assignment that satisfies the junction rule. Let me also again erase these. And then there's this, finally, there's this assignment where there's a current on that branch only. And so as a result, on this loop, there are currents in each branch, and on the other branches there are no currents. Okay, so we essentially have three possible ways of assigning currents to the circuit where each one satisfies the junction rule. So what we would like to do is to actually think about the possibility where all three of these exist, and we just take the superpositions of them. So I'm basically taking the superposition of all of these three different solutions. As a result, I'm going to assume that there's a current I1 on this loop. That's one particular solution, and there are no currents on the other ones. And there is this current I3 flowing on that loop, and both of them are together. And not only that, there is also a current I2 flowing in here. All right? So if I consider all of them together, in that case, I'm also, for each branch, I'm going to add the currents that each particular distribution tells me. And in that case, I'm going to get a current assignment that will satisfy the junction rule. So let me show in a separate place in here. I'm not going to show the details of the the resistors and things like that, these are not important. I'm just going to show the individual currents. So as a result, on this branch, the current towards right is I1, as well as on this one, it is I1 towards left, and whatever, it is I1 in here. On this branch here, on this branch, there is a current I1 flowing downward, and a current flowing upward, which is I2. I need to superpose them. But I2, I mean, the current flowing upward is I2, so therefore the downward should be minus I2. So I just superpose these two currents. So that's basically I1 minus I2. Okay, so the current in that branch would be in the downward direction, I1 minus I2. I'm just superposing these two currents. The expression that you write down in here depends on how you choose the arrow. If I choose the arrow in the opposite direction, so if I choose my arrow in the upward direction, in that case, I2 would be positive and I1 would be negative along that direction. So as a result, the current on that branch would be I2 minus I1. So on this branch, the current is I2 again in here. On this branch, it is I2 minus I3. So let me quickly write these details in here. So on this branch, it is I1 minus I3, and here it is I3, and so on. As a result, we can assign to each branch a current value, so it is quite easy to check that the junction rule is satisfied. For example, for this junction, we have these three branches. We have this branch, that branch where the current is leaving, and there's this branch in here where the current is incident to the junction. So if you write down the junction rule for that junction, so that's the junction rule, the current which is going in should be equal to the current which is leaving out. The current going in is I2 minus I3. And there are two currents which are leaving. So one of them is I2 minus I1. And the other one is I1 minus I3. Right? You can easily see that this equation is correct. So the junction rule is automatically satisfied. Another possibility is to have the loop rule satisfied. So as a result, instead of choosing the currents as the variables, we can choose the potentials as the variables. So let me use a white color for that purpose. So we just choose the potential of various junctions as unknowns. In that case, I don't need to check the loop rule, because the loop rule already tells us that the sum of the differences over a loop is equal to 0. That would be automatically satisfied. In that case, I need to write down only the junction rule equations. So as an example, let's just show this idea in here. So I'm going to start with this point in here. So I can also consider this as a junction. Actually, that point is not different than any of these two points. So let's remember that the potential is not well defined. Usually I choose a reference point and I choose the potential there to be equal to 0. So we can choose the potential in here to be 0. So people usually say that we ground that point. So that point, let's say that it has a potential 0. So that means this point has a potential 0. And that point as well. Okay, so if this point has potential 0, in that case, this point should have a potential which is equal to the EMF. So let me write the potential in here. So that's still not an unknown. So the potentials at these points are equal to EMF. And then we have this junction. Since I don't know the current that's flowing over this resistor, I don't know what the potential at that point is. So as a result, I just write this thing down as an unknown. So let's just call this potential as V1, and the potential at that junction, this is also an unknown. So therefore, this is also one of our unknowns. So therefore, there are two unknowns in that case, two unknowns, V1 and V2. And so as a result, I should be able to write down two junction equations, junction rules. And by using these rules, I can determine the values of these two unknowns. How do we write down the junction rules? You can think of it like this. I think I'm going to write down the junction rule, the first junction rule in here at this junction, right? So I'm just going to write this as an example. So in that case, I can see that the current that's flowing through that branch, plus the current that's flowing through that branch, plus the current that's flowing through that branch, I can sum them up and equate them to be equal to 0. So that's what I'm going to do. So I'll start with this upper branch in here. What's the current there? It's the potential drop, which is E minus V1 divided by R1. So that's my first current. And then what's the current in this branch? It is potential drop, which is V2 minus V1 divided by R5. And finally, what's the current in that branch? That might seem a little bit unusual because you might actually think that the V1 is positive, in which case the potential drop is negative in here. But in any case, if I move along the direction of the arrow, the potential drop would be 0 minus V1. So therefore 0 minus V1 divided by 2 is equal to 0. So that's one of the junction rule equations. So that's the first equation. There's going to be a second equation in here associated with the other junction, this junction in here. When you write that thing down, then you are going to have two equations. And since there are two unknowns, you can solve these two equations and then find the solution to this problem.